I'm now going to give you our headliner, Eric Niebler.
Hi. Great, thanks. Wow. I don't know, maybe I should take my glasses off so I can't see that I'm actually talking to like 700 people. That's really a lot of people, and I'm honored. Thank you guys for coming. It's really terrific. It's been a great conference, and I hope, as the last plenary of the conference, that this lives up to all the other great material. Okay, so what I'm going to be talking about today is ranges for the standard library. I've been working a lot on a library called Range v3, trying to bring the standard library forward into the world of concepts in C++, 14 and 17. The committee's taken some keen interest in this, and so this has kind of taken on a life of its own. I'm now bringing this forward to the standardization committee, and so the things that I'm going to be presenting here today are going to be things that you might potentially see in some future version of the standard library. So it's a very exciting time for C++, and it's super exciting for me to be part of this all. I'm going to be giving a talk that covers all of ranges. It's going to cover all the different parts. It's going to cover all, how they all work together. And it's going to be from the perspective of the application developer. I'm not going to be diving in to show you how it all works. I'm going to be showing you guys what the programming model is like, what it's going to be like in the future to work with the standard library and the range support that will be in the library, to build an application in a way that is declarative, composable, correct by design. Okay. And there's a little note at the bottom here. The idea for this talk was stolen from the D community wiki. So props to those D folks here. This was a really great example, and I had a ton of fun adapting it to C++ and ranges. And so I'm going to be working through this entire example line by line. I hope you guys have as much fun as I had writing this. It's really a lot of fun. So this is the goal. I'm going to be writing a calendar application, like a console application that takes in a calendar year and writes out to the console formatted calendar. You can look a little bit at the example, and you can see some of the problems that we might expect to come up. There's all sorts of weirdness in calendaring, days that start on, there's going to be lots of weird formatting, and we'll have to do white space padding and probably lots of offset computation, and it's probably going to get ugly and nasty because calendaring is ugly and nasty. But I hope to show as this talk goes on that it doesn't have to be ugly and nasty, and that it can actually be beautiful and declarative. So this is where we're going. Okay, here's the code. Everybody read that? Yeah? Okay. No, I'll go through it line by line. So, step one. Step one is going to be, obviously, we're going to create a range of dates. Dates for all the dates in a year. We want to be able to have it all in one big range that we can process. Now, what is a range exactly? A range basically is anything with a begin and end that return iterators or an iterator sentinel pair. I'll talk about that a little bit later. Where you can iterate from the start to the finish. So a container is an example of the range. It's not the only example, though, obviously. Okay. Before we talk about ranges, though, we're going to talk a little bit about dates. And if you went to Howard's talk, you got a glimpse of the future of how we're going to be doing dates in C++. It's pretty exciting. But here in the present, we use Boost when we want to do date time manipulation, because I don't want to have to write all that code myself. So here's an example of using Boost date time. You create a date, November 5th, 1955, important date, and we print that out to the console, and there, we've got a date. Great Scott, November 5th, 1955. Okay, easy enough. Now we can create a range of things using the range library that I just told you about. Here is a range that I call view iota. Has anybody used std iota? Oh, wow. Okay, some people actually do. So some people here actually know what iota does. It basically like fills in a block of memory, but counting integers. Like if you pass up view iota a 1, it'll fill a range with 1, 2, 3, 4, 5, 6. It'll just count. Okay. So that's what view iota does. It does the same thing. You pass it in some integers, and it's going to return a view of the integers, the range of integers from 1 inclusive to 11 exclusive. So it's a half open range. And if you print it out to the OStream cout, we get all the days, all the integers between 1 and 10. Okay. Simple enough. Now a range like view iota is going to be lazy. It doesn't actually return a vector containing all those integers. It's just going to spew out the next integer one at a time, and it's going to be lightweight, lazy, on-demand computation. That's the model for views, on-demand computation. So, like I said, views have a begin and end member. They're lazy sequence algorithms. These things are very lightweight. They're not heavyweight like containers. They don't own their elements. They generate their elements or refer to elements elsewhere. These things are composable, and we'll get to that a little bit later. The composability of ranges is where their real power comes from. And views, they don't mutate. So these are pure functional constructs. It turns out we'd really like to create a range of dates using view iota, but that doesn't work. The reason why is kind of nasty. Here's the error message we get. It says, the object passed to view iota must model the weakly incrementable concept. It's got to have pre and post increment operators, and it has to have a difference type. So the reason I show you this is not because I want you guys to debug my code for me, but just because this is a little taste of what we can get in the future with the concepts language feature. Now, probably a lot of you guys are might be familiar with concepts and what concepts are. But basically, it's a way of saying in code what the expectations are on the types that you pass to a template. You say, okay, I pass this thing, something that has to be incrementable, and if it's not, I want to know about it, and I want to be told in a way that is human readable and friendly, unlike what you get from the STL today. Okay, so pay no attention to that man behind the curtain. This is like a really ugly hack here. I'm just going to open up the Boost namespace. I'm going to jam in the operators that I think Boost Datetime should have provided in the first place. This is not nice. Don't do this in general. But it's just to make the code compile. And it does. Once we do that, now we can get a range of dates using view iota, which is nice. I've already talked to Howard, and I've stumped for adding incrementability to the dates in the library that he's building. So he's noted it. But in general, it's not nice to open other people's namespaces and jam stuff in there, so don't do that. Step 2, we've got a range of dates, all the dates in the year. Now we want to group those things into months. We're going to do that with something called view group by. So we have this function, dates in year, returns a range of all the dates in a year. And we pass it to this thing called view group by. Group by, what it's going to do is it's going to carve up a range into a range of ranges, where each subrange is comprised of elements for which this predicate returns true. And this predicate here, this lambda that takes 2 dates, will just return true if both of these dates are in the same month. So in goes a range of dates, out comes a range of dates, where the inner ranges represent months. Okay? That's what's going on here. Now, this last line here, the range 4, we loop over all of the months, and then we print out the first day in each month. Now, I've gotten questions about, like, why don't I use the range for loop here? And the reason why is because, as it turns out, the months object has an end iterator that isn't actually an iterator, it's a sentinel. So in my view, my vision of the future STL, the begin and end of a range, those types, which currently have to be the same today, I think they should be allowed to differ. So that's a change that I'm proposing and hasn't been accepted yet. But it means that these things can't be used with the range for loop, the built-in range for loop, because that expects begin and end to have the same type. That's the only reason there. One thing I should have said from the beginning is if anyone has any questions at any time, please just raise your hands, wave or shout me down, and I'll be happy to answer any questions. Okay. Oh, a question over here?
Yeah, I'm just wondering, what's the bitwise OR here?
Okay, the question was, what is the bitwise OR? That's a good question, thanks. The bitwise OR is range composition. It's a range composition operator. So if you are familiar with the Unix command line, where you can run a command and pipe its output to another operation, and then pipe its output to something else, and then to something else, that's what this is. I basically hijacked the binary OR operator to make it do range composition. So you take a range, you pipe it to something that's going to adapt to the range, you get another range. You can pipe that onto yet another adapter and another adapter. Okay? Thanks, good question. So another question here?
Why does group by have to take two arguments? Because if you look at C#, for example, they do a group by with just a single argument that returns. You could return a month and use that as a key in a key value store instead of compare the keys. Why do you have to have two arguments?
So the question was, why does why does the predicate need to take two arguments? I found that it was more general to take two arguments and return a Boolean than to have a unary function that returns some sort of a key and then put extra smarts in the group by view itself. I can't think of an example off the top of my head, but I do know that when I wrote this, I looked at the C# version. Every language has some variant of group by, and I looked at a bunch of them and decided to take what I thought was the most general. Other question? Okay. Cool. So we're just going to clean this code up a little bit. Oh, yeah, here's the output. You get the first day of every month in the year. Okay. So that group by expression, we could just lift it out and we could move it into a named function. We say by month. And we put our group by expression in there. The usage is, it changes the usage and it cleans it up a little bit. We're going to use this technique quite a lot in this code to make things simpler, to group complicated actions and view adapters, and to give them a name by sticking them in a function. I'm using, all right guys, who's calling me? Sorry. So where was I? Right. Just using C++ 14's what is it? Deduced return types. So I don't have to say what the return type is anymore. I could just say auto, the function name, returning an expression. And the return type of that function is deduced from the return statement. Really nice. Comes in really handy in code like this. Okay. So like I said, I'm hoping to get a lot of this stuff into the standard. These are the ones that are in the range v3 library today. These are built-in adapters that you can just use out of the box. Things that you might expect to find, you know, like concatenate ranges and delimit ranges with either, you know, a predicate or a sentinel value. Yeah. So the idea is that you should have this toolbox of range adapters at your disposal, things that you could just plug and play with. Okay, so we've grouped a year into months. Step 3 is going to be much the same. We're just going to be grouping the month into weeks. And here we have by week, which is going to take a range of dates, and this is going to be a month, and it's going to group all of those dates into weeks. And we use the week number API on the date object to find out what week number that date is in. That'd be like 1 through 52, because there's 52 dates in a year, 52 weeks in a year. And then we're going to be transforming all of our months by carving them up into weeks. So we use transform on every month. This is in the middle here. View transform every month, carve it up into weeks. And now we have this statement here, dates in year by month, month by week. By month turns a range of dates into a range of dates. And month by week takes a range of dates and turns it into a range of ranges of dates. So things are getting pretty interesting now, right? So now we can loop over the months, and then in each month we can loop over the weeks, and each week is itself a range of dates. So we can transform that range of dates into a range of days, a range of integers representing what day it is in the month. And we could print that out. And when we do that, we get this. Well, this is looking quite a bit like a calendar already, isn't it? And we haven't really done all that much. So this is pretty cool. Obviously, though, the weeks are not formatted correctly, so we need to work on that next. The next step is going to be formatting. And I kind of hate, oh yes, question.
Why is the weeks thing at the end on the next slide?
Why isn't the weeks thing on the end?
Yes, the month by week. Why isn't it? I mean, you've got a month now.
Got a month, yes.
So I sort of feel like we've gone into weeks at the end, and now we're going to iterate through some months after we've made some division.
Okay, I see what you're saying. Yeah. So what we did was we carved the year into months, and then we transformed each month by carving each month into weeks. What you still have, though, is a range of months where each month is a range of weeks. So when you iterate over the outer thing, you're still iterating over months. You're not iterating over weeks. Did that answer your question?
Yes, that's what I thought, but I'm going to have to think about it for a while to see, what the mechanism is.
Okay. Yeah. Any other questions about this? It's getting kind of hairy now. Yeah. Okay. So this is what we have so far. We're going to have to do string formatting now. In particular, we certainly will need to put each day into a field, say like 3 characters wide, And we're going to have to put some white space at the front of the first week of each month. Once we do that, things are going to line up and look quite a lot like a calendar. So I hate string formatting, so I use a library to do it, and it's boost format. And the problem, boost format is good, but it means that your format strings, like printf, looks like a bunch of gibberish if you don't know the syntax. So I'm going to throw some gibberish at you and wave my hands and tell you that it does what I say it does. And if you don't believe me, you can go check out the boost format documentation. It's actually not bad. So here's how you format a day. I want to format a day into a field that's 3 characters wide. That's what we do. You pass in a date, you pull out the day, you format it, you return a string. It's a function that takes a date, returns a string. Now, okay, this one takes some work. Formatting weeks. This is going to be an operation that takes months. It transforms each week in the month by formatting the week. And the first thing that we do, let's look at the last line first. We're going to take the week and we're going to transform it with format day. So we have a range of dates. Format day is going to turn that range of dates into a range of strings. And then we're going to join all the strings together, and I'll talk a little bit more about that later, into one big string. So this formats that week and glues it all together into one string. And now the only thing we have to worry about is like padding, white space padding in the front. Yeah, question in the back. I mentioned concatenate. Why didn't I use it? Right, so that's a really good question. The reason I didn't use concatenate is because we're going to be passing the result of this operation to this boost format operation. Boost format was written before I wrote my range library, and it doesn't know about lazy ranges, it knows about strings. So I have to transform this range of integers, or a range of strings, into an actual string so that boost format knows what to do with it. But good question. Yeah. I would have loved to have done this lazily. I hate having to do dynamic memory allocation for no purpose. It just makes it all slow. And so the second line from the bottom is just the formatting. Right? I'm going to take, like, what day of week is the first day in this week? If the week starts on Sunday, I don't need to pad anything. If it starts on Monday, I need to add some padding there. So I use the day of the week times 3. That's how wide each column is. And I use that to build a string of space characters. And I stick that in, and I use boost format to take this whole string, format it into field that's 22 characters wide, and write that out. So that's what this elaborate transformation is doing. Okay, and layout months now, we get in is a range of dates. These are months, a year of months, and we're going to transform each month by carving it into weeks and formatting each week. So let me go back and talk about action join. We've been talking so far about lazy view operations, and like I said, right, I didn't use a lazy operation. I could have used concat here, but instead what I did was I used something that operates eagerly and actually does allocation, returns a container. So it's a totally different class of operations than the views. Actions, these are eager algorithms that operate immediately. And they can operate and return containers. They are also composable, just like the views, but these things can mutate also, as opposed to the views, which can't. So here's how they stack up with the ranges, with the views. Views are lazy, actions are eager, views are lightweight, actions can return containers, so they're heavyweight. But they're both composable. One can mutate and one can't. Here are the built-in actions. You know, things that could mutate containers you would expect to find here, like erase and insert. We can slice containers. We can split them up into sub-containers, et cetera, et cetera. Yeah. We can make them unique. We could sort them. So we could take some data, pipe it to a sort operation, pipe it to a unique operation, have all our unique elements in a container. Yeah, that's what you use range actions for. Sure. So why is take an action and not a view? Take is both an action and a view. So sometimes you want to do it lazily. Sometimes you want to do it immediately. Sometimes, if you want to do it immediately, you want to take the first n elements of a vector and return a vector. That can be a useful operation. Yeah. Good question, thanks. Okay, so here's where we are so far. We can create a range of dates. We can carve it up into months. We can lay out the months. When we do that, we get a range of months. And in each month, we get a range of strings representing each week. And we could write them out. And when we do that, we get this, which looks a lot like a calendar right now. Okay, terrific. You can see we need the month headings, right? We need to find out what month each one is. And we're also going to need to do some padding, right? If you remember from the beginning, each month was going to be laid out side by side, right? And if they're laid out side by side, then we have to make sure that they take the same amount of vertical space, each one. So some months are longer than others, take up more vertical space than others. And for the ones that take up less vertical space, we need to add some white space. So that's what we're going to be doing. Okay, so let's take the month title first, whose date time has this great function called month as long string, which gives us the month title. So I don't have to worry about like localization or anything like that. So here's a function that takes a date, returns a string representing the name of the month. And now here's view concat. I use view concat in the transformation. So before we just had month by week format weeks, but now we want to stick an extra row at the top which represents the month title. So I could use view concat with a single element. Concatenates two ranges. I have the month title, I need to turn it into a range of one element containing the month title, so I can concatenate it with the next range. So that's how I do that. Okay. And when view single, like I said, creates a one element range. And concat lazily concatenates ranges, as you might expect. And so that's what we get now. And padding empty lines, we use repeat n. First thing we do is we count how many elements are in our month, right? It's anywhere between 4 and 6. We want to make sure that they are all 6. So we want to count how many weeks we have in each month. That is, how many lines each month takes. And figure out how many lines of padding we need. That's 6 minus the count. And then we just repeat an empty string that many times, 0, 1, or 2 times, and add that to our concatenated month, formatted month. And now we are guaranteed that all our months are going to line up when we stack them side by side. Okay. Okay. So let's, pause and take a breath here and see where we're at. We've got a year, which is a range of months. Month is a range of strings. Each month has exactly 7 lines. By month and layout months, reusable. They work even on infinite ranges, which is kind of nice. We got that for free. If we pipe in an infinite range of dates, it'll just keep spitting out formatted months forever. It wasn't part of our initial problem specification, but it's nice to have a feature like that for free. Okay. Incidentally, I want to make a point here. Has anyone seen so far in my code an if, or a for, or a while? Not a single one yet. It's kind of interesting. Okay. Also, has anyone seen any state? What state is there that is getting mutated as this is getting done? Right. No mutable state, no branches, no loops. Interesting. Yeah. Okay. Side-by-side layout. We need to get from the left to the right. And it's actually a little bit easier than it looks, I think, at least conceptually. Because what we have is a range of ranges. That is, we have a range of months. Each month is a range of strings. Each string is a week. You can kind of think of a range of ranges as a matrix, right? So we want to get from the matrix on the left to this matrix on the right. Who can tell me how to do that? Who hasn't watched this video on YouTube before?
You slice and then transpose the bits.
You slice? You slice how?
Cut horizontally, and then you have several matrices. You transpose each one of them. And
Okay, yeah. You slice, that is, you kind of you grab a chunk of the first three, right? And then you transpose the rows and columns of the first three, and then you do that for the next three, and you glue it onto your preceding one, and then you grab the next three, you transpose and glue, and so on. You can keep doing that, okay? And if you do that, what you do is you've transformed this range of ranges into side-by-side months laid out. It's kind of neat, right? This solves one of the fundamental problems that we have in this problem, which is that the console output is serial. And that's great when you want to write things out that are already in the order that you need them to be, in the display. But when they're not, you have to figure out, right, how do I, work around this impedance mismatch? And we do that lazily by doing this trick with chunking and transposing. Chunk and transpose. So this is just to repeat what was said earlier. We chunk the months into groups of threes. For each group of three, we transpose the rows and columns. We join the chunks. Then we can reach in and join the strings of the inner ranges. That is, these 3 months side by side. We'll have 3 strings. We can glue those all together into one big string. And then write all that out to the console, and then take the rest of the day off. So, first step is to chunk, right? When I wrote this example, there wasn't a chunk adapter in my range library, so I had to write one. So, I'm going to show you how I wrote the chunk adapter, because sometimes there isn't a tool in the toolbox that meets the task at hand. Right? So an adapter, right, who's read the Gang of Four? All right, who just has it sitting on their shelf unopened? Yeah, that's me. But adapter is a pattern. It's a design pattern. The Gang of Four, they restrict their adapter discussion to when you're adapting something with one interface to something with another interface. In this case, what we're adapting is behavior, because we're going to keep the same interface. We're taking in a range, right? And we're going to spit out a range which has exactly the same interface, but it's going to have different behavior, right? We're going to take in a range, and we're going to spit out a chunked range, which is a range of ranges. So we're creating structure. Okay. So it's going to look basically like this. We're going to have an outer range that encapsulates an inner range and changes its behavior. Your inner range has a begin and end, right? And your outer range has a begin and end also. Your outer range's begin is going to return an iterator. Its iterator is going to wrap an iterator from the inner range. And this outer iterator is going to have iterator operations on it, the ones that we're familiar with. You can dereference it, you can increment it to move to the next element. But those two, operator star and operator plus plus, all the way on the right there, that's where all the magic is going to happen. That's where we get to specify how our behavior is different than the range that we've wrapped. So we're going to want to find a really concise way of specifying how this behavior is changed without having to write all of the boilerplate of I'm going to specify this range over here, and generate this iterator type, and I have to completely specify and write out all the iterator functions. Who's written an iterator before? It's really a lot of boilerplate, right? Really a lot. So we want to be able to generate all of that stuff automatically. And so here's how our behaviors are going to change. The chunk adapter, when you dereference its iterator, rather than returning an element, we want it to return a range of elements. N elements, that's the chunk size. And when we increment that iterator, we want it to jump over n elements. So we only want to specify that behavior, and we want to get everything else for free. And to do that, we use a range adapter template from the range library. We have a chunk view that inherits from range adapter, which is going to wrap a range. This here is mostly boilerplate. The bit that's interesting is this adapter class. That's where we're going to put our new behavior, where we specify the updated operator star and operator plus plus. And everything else we'll get for free. So let's put that over there, and let's look at this. Here's the adapter. We can store some members, the end of the inner range. And then we implement current and next. Current and next is where the behavior for operator star and operator plus plus are going to come from. So you can see that current is using view take to take the next n elements from the underlying range, taking care not to go past the end of the range if the range is not evenly divisible by n. And then next is just going to advance the input iterator that many steps, taking care again not to go past the end. So this is how we write a new adapter type. It's not that hard, really. It's not a lot of code. Now we need to make it easily usable. We use this function called makePipeable. Right? We want to be able to pipe things along and have it generate adapters of adapters of adapters. So here's how we write chunk. MakePipeable is a fun higher order function that kind of hurt my head to write, and I'm sure it would hurt my head to try to explain it, and we'd probably run long, and I want you guys to make your lunch. So I'm going to kind of skip a discussion about chunk, but there will be slides you can download for how that all works. Once we have the chunk adapter, we can chunk ranges. So here's a vector, we can chunk it, and we get a range of ranges. Okay. Cool, so now we have chunk. Now if you remember our steps were we need to chunk, we need to transpose. So step 2 is transpose. And here's where I got stuck. Because I didn't really know how to transpose a range of ranges. It wasn't clear to me at all. Right? I knew if I had like all of this stuff in memory, right, and I had random access to it, I could just jam stuff around wherever I wanted, and I could transpose a range of ranges in place pretty easily. But when things are being generated lazily, when I have a lazily generated range, and each element is itself a lazily generated range, then how do you transpose something like that? That was an interesting challenge. I'm just curious, can anybody think of a way to do it? Does anybody? No? Yeah, it's tricky. Yeah? Could you use zip? How would you use zip? It was rhetorical. That's actually a really interesting question. And the discussion of like why you can't use zip here would be a really interesting one. But I think it's best done after the talk. Yeah. Yeah. Zip gets you close. I'll give you that. Yeah. I sat on this for a couple of days, and then I thought, aha, I think I know a way. So one thing that we can do is we first do an interleave. Let's traverse the elements in this order by doing this round robin sort of visitation, okay? And what we're doing now is, okay, we start with a range of ranges, we erase that structure, we flatten this structure in a very particular way. So we get a single range instead of just a range of ranges. We get a single range, January, February, March, then the first week of January, the first week of February, the first week of March, like that. Okay. Can anybody see what the next step is? What was it? Chunk. Great. Then we chunk. We've already got chunk. We just wrote it. That's terrific. We chunked that data structure, and now we've transposed a range of ranges lazily and on demand. Neat. Okay. So we're going to have to write this interleave operation. I didn't have an interleave adapter at the time, so I had to write one. And to do that, I used range facade. Facade is, right, when you don't want to write all the code out, there's too much boilerplate, you want to specify just a couple of functions and have everything else generated automatically. So here's how it works. Rather than writing the iterator interface, we write current, next, and done. We could write those from scratch. This isn't an adapter. We're not like adapting an underlying range. We're building a range from scratch now. And we want begin and end to be automatically generated to return an iterator and a sentinel. Okay. So really, in order to implement a range, you only need to specify 3 functions: current, next, and done. You can implement more if you want. You can implement equal, prev, distance to, and advance. If you implement equal to, you get a forward iterator instead of an input iterator. If you implement prev, you get a bidirectional iterator. If you implement distance to and advance, you get a random access iterator. So this is the iterator that gets generated. It's going to store one of those cursor objects, and it's going to implement the full zoo of input iterator operations. Okay. Now, for interleave, here's the behaviors that we're going to want. The current element will be to return the ijth element. Right? And next, we'll bump j, and if we've reached the end, we want to loop down to the next one. Bump I and set j to 0. This is how we do interleaving. Everybody see that, more or less? No. Okay. Go. So, now we use this range facade. And just like the adapter, this part is mostly boilerplate. We have this thing here, which is where all the action goes on. Okay. Our cursor. So here's the cursor. Here in current is how we return the current element. It's basically an ij computation. We have a range, we index into it. We dereference that range of iterators, we get back the current element. And then next, we're going to be bumping I. And if we've gotten to the end of the current range, we increment and go back down to 0. We increment all the iterators, and then on our next element, or on our next access, we're going to be accessing the first element of the next range. Done is interesting and clever. I had to use mismatch algorithm from the STL. I'd never used that one before. To find out whether any of the ranges in our interleave have terminated. We kind of we stop at our earliest opportunity and then bail. And then equal, we can test to see whether 2 cursors are equal. That gives us whether 2 iterators are equal, which is important for forward iterators. Here's our interleave adapter, pipeable operator. And now we can take a range of ranges. This is this thing with structure, and we could erase the structure in a very certain way. This view iota, that gives us a range 0, 1, 2. And we get 3 of those, 0, 1, 2, 0, 1, 2, 0, 1, 2. And we flatten it, and we get 0, 0, 0, 1, 1, 1, 2, 2, 2. So we've interleaved the elements. Yeah, question? Okay, so the question was, why do I have this vector, which is going to be in the iterator and it's going to be expensive? Can we do something with pointers and referring back to elements? We can't do anything clever with pointers. The reason why is these are lazily generated ranges. Once you move on to the next element in a lazily generated range, that old element is gone. And you can't, if you are left holding a pointer to it, you're left holding a pointer to invalid memory. So an awful lot of work with ranges is done by value, so that you don't have to worry about whether your data lives in memory or whether it's being generated on demand. Because very often when you're doing writing code like this, stuff is getting computed on demand. In fact, you want things to be computed on demand. You don't want them to live in memory. Right? Think, for example, like if we were operating on an infinite range of data. And obviously, you can't keep an infinite amount of data in memory. Yeah. Okay. Great, we've got chunk, we've got interleave. That means we have transpose. We get that for free. So we just take ranges, we interleave them, and we chunk them. And so now I can transpose a range of ranges. We can take a range 0, 1, 2, 0, 1, 2, 0, 1, 2, and get 0, 0, 0, 1, 1, 1, 2, 2, 2. Transposed lazily. And now we're pretty much done, actually. That's all we need to do. The rest of these steps, well, we know how to join, and we know how to print. Not even going to bother showing it. Here's the final solution. Dates in year, we chunk it by month. We lay out the months. We chunk it into the groups of 3. We transpose the months. We join, and join again. For completeness, transpose months just as a transform and a transpose. And join months is a transform and a join. This is going to be like we've transposed groups of 3 months, then we transpose and join all of those things together. And then we reach in and we join all the weeks into single lines. And we get our calendar. So if anyone was counting, how many loops were there in this program? Okay, there was
No explicit loops.
I'm not using range 4 anymore. I'm using std copy, or my range copy. Okay. So now, how many loops? None. Yeah. No loops in this program at all. Yeah. And if I counted correctly, there's exactly one if statement. Yeah. So let's look again. So when I said earlier that ranges are composable, I think by now you guys get the idea. You can pipe these composable operations, get ranges that are transformed and transformed and transformed. A lot of this code is reusable. We wrote chunk, we wrote interleave. Those have nothing to do with this problem in particular. Right? Those can be reused over and over again. This works with infinite ranges. If I pipe in an infinite range of dates into the front, what I get is like a constant stream of formatted months. It just spews formatted months endlessly. Also, this is the only place in the entire program that 3 appears, right? In this one place for showing 3 months side by side. If I change that in that one place to 4, I get 4 months side by side. Right? I could make that a command line parameter if I want. No. I got that for free. No loops. This code is correct by construction. And what I mean by that is, like, I don't really have to do a whole lot of work to prove to myself that it's correct. I built it so that it's correct. Right? There's no state that's getting mutated that I need to reason about. No loops that are doing any complicated things. Really, it's the state that gets you with bugs, right? When you have branches and state, right? Then you have to worry about this explosion of complexity. So many states that my program can be in. Now I need to worry about like whether one of those states is an erroneous state. If you write code where there are no states and there are very few loops and branches, where do the bugs come in? So here's the final solution again. I coded in, I guess that's yellow, code that has something to do in particular with this problem, and code in green, stuff that has nothing at all to do with this problem that's totally reusable. That's chunk and transpose and interleave. It's kind of nice that we get to lift all of that code out. We could put it in a library and reuse it. This is how I like to write code, but I'm a library designer. It tends to be how I think. Okay. So ranges and standardization. You might be thinking like, okay, that's all great, but when do I get it? So what's been proposed and what will be proposed? Say the range concepts, which I didn't really talk much about, have been proposed. And the range algorithms have been proposed. That is, algorithms that accept ranges instead of iterator pairs. That's been proposed. But the adapters, the actions, the facade, and that range adapter helper class, I haven't proposed those yet, and it's just for lack of time. So, but I will propose them, and that's on my agenda. So where are we so far? So I made an initial proposal back in October of 2014, and it was favorably received by the committee. So I went ahead and did a more refined proposal, which has been under review by the library working group in various telecons. Right now, we're doing this detailed wording review, and I've been drafting other range proposals. So today, actually, is the mailing deadline. I have to get my papers in. I've got another paper on proxy iterators. Proxy iterators, who's familiar with like the vector bool problem? Yeah, a lot of people. Vector. You know not to use it. Okay, then you know enough. Vector bool has these things called proxy iterators. When you dereference a proxy iterator, you don't get a bool, you get something that tries very hard to look like a bool. And that causes all manner of problems, the way the concepts and the algorithms are currently specified. So I would like to change how they're specified so that proxy iterators are fully fledged members of the STL hierarchy. That's going to be really important when we get to view adapters like the zip adapter, which, when you dereference a zip iterator, is going to return a tuple of references, which is a proxy type. So if we want the zip view, and I think we do, then we have to solve the proxy iterator problem, which is why I'm tackling that now. So hopefully in October, in the October meeting in Kona, we will vote the initial draft into a TS. TS is a technical specification for people who are not committee wonks here. And then we're going to review the wording of the other proposals, the proxy iterator paper. And in the next year or so, I hope to make further progress on even more papers. I want infinite ranges to fit nicely into the hierarchy. I want those views and actions that I talked about, the views and actions that actually make this particular example work. Yeah, actually write a proposal for all of that stuff. And the facade and the adapter class also. These all need papers, and it all takes time. At some point, the TS will be approved, and it'll start showing up, and platform vendors will start shipping it. And then at some point, that TS is merged into C++ XY, and it'll become STL2. So that's the idea. Maybe you guys weren't aware that we were actually working on STL2. That's what this is, I think. So if you guys have pet peeves about the current STL, you can send them to me. I'll try to integrate them and see what we can do. So here's where you could find out more. Here are the papers that I've been working on. This first one is a very high-level design rationale, comparing and contrasting to other range implementations like the D range implementation. The second one is kind of like what you could read if you're having trouble sleeping at night. It's the standardese for what I'm proposing. Probably more interesting to this crowd, though, is the actual library that you can use today. And that's where you can find it. And it works on any conforming C++ 11 compiler. That, by the way, excludes Microsoft's compiler. All of them. Microsoft's compiler. Yeah. 2015, I think, is the most recent one. Yeah. No. What's it missing? It's missing Sphene for expressions. That's the really big one. Because I use Sphene for expressions to emulate concepts. And Clang and GCC do quite a good job with it these days, but not so much. Although I think the latest release of GCC has got real problems. So GCC 5.1, is that the latest, or are they up to 5.2 now? Can't compile my code. Need to figure out why. We'll work on that. Yeah. Okay. So this example is also online. It's in the examples directory. So you can find that and hack it, play around with it. I think it handles, you can specify an infinite range and you could watch the formatted days go by. So I think that's all I've got. I finished a little early. I'm happy to take any questions you guys might have. Yeah, question? So, okay, the question was, I have an operation called distance. And there's an algorithm in the standard library called distance. And so the distance helper that I have is just a range-based version of that algorithm. Rather than passing, you know, a begin iterator and an end iterator to std distance, you could just pass the whole range itself to range distance, get the distance of the range. There is a notion in my library of ranges that are sized. So for instance, vector that has a size member function, or in particular list. Like some implementations back in the day, list size was not order 1, or maybe it was, right? So, right, I said that wrong, sorry. Today, list size is order 1. But if you simply took out the begin and end iterator of a list and passed it to std distance, that's an order n computation, because you have to walk the entire list to compute its size. Whereas if you just ask the list, how big are you, it can tell you that in order 1. So range distance is smart enough to make that order 1 instead of order n. Yeah. Cool, thanks for that question. Yeah. All right, any other questions? Yeah.
Yesterday at Louis' talk, he showed at the end of his presentation on HANA how he'd taken your proto library and basically fed HANA stuff into it, and suddenly proto went from being a dynamic executed library to being a purely const-expr implementation, which I was wondering, firstly, were you aware of?
No, I was not aware of that at all.
Yeah, he was amazed that it just worked. No modifications required. So
I'm kind of amazed too.
Yeah, he took your hat off to you. So the question then was that if you're not aware of that, I suppose this kind of makes this question a bit moot. But Louis was showing how to basically create the same programming API between constant time computation and runtime computation.
Right.
And I know he's not here anymore because he had to go back to Canada, but it was interesting as he was showing how to modify proto to do this, that it kind of immediately then opened the question of what is in the way of ranges being able to do the same. But of course, if you haven't seen this, then you probably can't answer that question. But would you say, I'll put a different question then, would you be keen on the idea of constant compile time programming having the same specification looks very, very similar to, so instead of writing 1, 2, 3, 4, you might write 1_C, 2_C, and so on to turn them into constant expressions. Would you be keen on that, or do you think that's a bad idea?
So using ranges and range algorithms to operate on compile time ranges?
Yes.
I think that's an interesting idea, and you could actually go quite far with it. In particular, like some of the std algorithms could themselves be const_expr, and you could pass in, say, like a const_expr initializer list or whatever, and operate on that and get a result of compile time. There are problems with that, though, because some of the algorithms cannot be const_expr. Some can, but only if you implement them a certain way, and so that restricts implementer freedom. And sometimes it happens that algorithm implementation that is const_expr friendly is less efficient than a different algorithm that is not const_expr friendly. So figuring out where to use const_expr and where to leave it off is actually a really tricky problem.
I think Louis got a paper coming on the exact problem, on ideas of, this is a problem and how should we fix it is basically what the paper asks. But it's not my area, so thanks for the answer.
I mean, my answer is, here be dragons. Yeah. Yeah.
Thanks.
Yeah. Oh, yeah.
You showed how in your program there was only one place where you had a 3 in main for chunking the number of months.
Yeah.
I was just curious, if you were to put a 0 in there, what would happen? And at what level does that get caught as a problem?
So at what level does it crap out if you put a 0 there? Since I wrote this code, I've promoted chunk to being a full-fledged member of my range library. And the argument that you pass to chunk has to be greater than 0. So where it would die is in the constructor of the chunk view. which will assert that the chunk size is greater than 0. So it's a runtime check. Yeah.
Hi. I noticed a number of the views and actions like repeat N and take where you're actually taking numeric parameters, and chunk is actually another example. Have you considered making versions of those that take those as templated compile time constants?
Right, so I have thought about that actually, and it's an interesting question. Where does that give you a speed up and where is it a benefit? In particular, it's interesting with transpose and with interleave. The interleave iterator needs to store a vector of iterators into the ranges that it's interleaving. Vectors obviously are expensive, dynamic memory allocation, and you don't really want to have iterators that hold on to dynamic memory and have to copy them because iterators get copied all over the place. So making the size a template parameter would make it possible to use a std array instead of a std vector, and that would have much better performance. It impacts the usability a little bit, though. Transpose right now is very nice because you don't have to tell it how big is the range of ranges that you're passing in to transpose. It can compute it. And then just do the transposition based on that runtime information. But you'd have to change the interface to transpose to say, I'm transposing something, and oh, by the way, here's how many columns are in this thing. And then if you pass in something that doesn't have that many columns, well, then what do? You have to figure out an answer to that. It's not impossible. You just have to figure it out. But you know, for this example, I wanted to keep it as simple as possible. But yeah, it's a good question.
Thank you.
Yeah.
So heard this presentation a while back, and when I first heard your suggestion of using sentinels as an alternative for end iterators, it struck me as completely brilliant.
It wasn't my idea, by the way.
Okay, well,
yeah.
so whoever thought that up, that's perfect. And during your presentation, it sounded like there may have been some pushback on that. So what is the state of sentinels versus end iterators, or did I misunderstand your presentation?
So there hasn't been pushback on the Sentinel idea. In fact, I first presented this idea at, it was about a year ago at the Urbana meeting of the committee. And we all took straw polls. This was in an evening session, so just about everybody was there. And I really expected that to get the thumbs down because it's quite a radical change from where we are today. But really, it was almost unanimous. Everyone was in favor of Sentinels, which really made me happy and kind of blew me away a bit. It seems like that's not a controversial change at all.
Great.
So I'm really looking forward to seeing that in the future.
Yeah. Thank you.
Yeah. Yeah, question.
Hi, I have a question about infinite ranges. So to my understanding, they can represent streams of data. And you would, for instance, we would like to perform some computations on this data on demand, and you would prefer not to keep too much of that data in memory because it is infinite. So my question is, suppose you would also like to perform those on-demand computations asynchronously. I'm wondering, is there perhaps some ideas overlap between this library and libraries like reactive extensions for C++ or RX CPP, which seem to support just that?
Yeah, I actually don't know a whole lot about reactive programming, so I can't really speak to that part of it. But I do agree with you. There's lots of potential with the interaction between ranges and asynchronous programming. In particular, one thing that I would like to research is the interaction between ranges and coroutines.
Right.
Because these things, I mean, it seems natural to me. Like certainly you could use a coroutine to generate an infinite stream of data very easily.
And in terms of standard, one could think of a reactive extension a little bit like STD future, but you have an STD future of an infinite stream. So it's essentially a future stream that keeps arriving and doesn't keep terminating. And then you might want to perform asynchronous computations on that. So that's
Yeah.
the link.
I think that sounds like a natural fit for the work that I'm doing here.
Great.
Yeah,
Great. Thank you.
absolutely.
When you were asking about how to implement interleave, and other people have said, well, it keeps the state. But the first thing that I thought of there, though, is that if you have basically a range of ranges or a stream of streams coming in, or a queue of ranges, basically, I want to take the first one from the first thing in the queue and then take all the rest of that and stick it at the end, right? And I take the next one and take this and stick it at the end. Is there a natural implementation of that sort of take the first thing and stick it at the end of my range operation? Or is there some reason that you didn't implement interleave like that, so you didn't need the temporary vector?
There's a couple of reasons why I didn't implement it like that. First of all, can you transpose a range of ranges that are infinite?
Yes.
Yes, you can. So what does the stick it on the end operation mean for an infinite range?
Well, I don't think you can transpose an infinite range of ranges, but you can transpose a range of infinite ranges.
You can transpose a range of infinite ranges.
A finite
Yes.
range of infinite
Yeah.
ranges just by
Yeah.
sticking it at the end of the finite range. But if you have an infinite range, even of finite ranges, I think transpose just means take the first one from everything forever.
Right.
Right? How would you
Exactly.
ever
Yeah,
get the
exactly.
second
Yeah.
thing, right?
Right. But the other thing, the other problem with the stick it on the end thing, you have a range of ranges. The stick it on the end needs to be done lazily, right? That means you adapt it with a concatenate adapter. That changes its type. And you can't store that in place. That's not an operation that a single object can perform. It would then need to return a new object with a new type. So every time you take an element off of this interleaved range, your range changes its type, which is impossible. Yeah.
I'm not sure I see it, but I somewhat believe it.
Yeah. It's different if we were dealing with just lists of things. Then absolutely that's a viable implementation approach. But with ranges, when you adapt something, like concatenate, then you're changing the object's type. And you have to work within the type system, which can be a bit of a straitjacket in times like this.
So, sorry, follow up, I guess, but in your example, in the calendar example where you had like a range of days that you got from, originally you got it from IOTA, and then if I were to concat two of those with uconcat,
I'm sorry, repeat that?
So if I have like a range of days that I got from view IOTA, and I put that in some auto variable, and then I have uconcat of that with itself, let's say, and I put that in some variable, their decal types are now different?
Different, yes.
Okay, I wasn't actually getting that, okay.
Yeah. Because concatenate, what it does, it works lazily. It doesn't actually do the concatenation, because that would be an eager operation. What it does is it holds on to the two things that you are concatenating, and then while it is iterating, it gives you an iterator that is smart enough when it reaches the end of the first range to know to jump to the start of the second range. So it has to have a different type than the things it's adapting.
So I get a pattern that I've been and some of my coworkers have been using in our code bases where we regularly have to interact with sort of the what I'm going to call the C iterator, which is like the get first, get next, et cetera, pattern.
The Java iterators.
Yeah, or Windows directory entries, get pwent in POSIX, those sorts of APIs. And those map really, really well to input iterators. And it is a lot of work to get any of the other iterator guarantees. You have to store a lot of state in your iterators. I guess two questions. One, how much of all of this works with those bare minimum input iterators? And two, do you foresee sort of a generalized input iterator to more complex iterator that will help store that state adapter being a useful thing?
Okay. To the first question, like how much of this stuff works with input iterators or input ranges? A lot of it does, not all of it. Just like with the algorithms in the STL, some algorithms need stronger iterators than that. You know, you can't pass an input iterator to sort and expect anything reasonable. I think the group by adapter that I showed needs forward. Does not work with input. Bit unfortunate, I've tried. Maybe someone smarter than me can figure that out. But I think a lot of what I showed today works with input iterators. And of course, all of the algorithms, you know, are just like the STL algorithms. So whatever they expect. You know. Then the second one is, your second question was how much of this, what I've showed today, like helps with the boilerplate and the state maintenance? Not at all. So you would need to do that yourself. The only difference is rather than writing an iterator with a fat interface, you could write a cursor with a much smaller interface and have all that other stuff automatically generated for you. Yeah.
Thank you.
Yeah.
So I found when I was experimenting with ranges, I had to change my way of thinking a little because in the standard library right now, every container is finite. And so reversible is synonymous with has a bidirectional iterator. But that's not true of ranges because they can be infinite. So you need to find the end before it's reversible. So it needs to be bounded and bidirectional. So my question is, had you thought of, as far as I know, reversible is not a concept in the range library right now, but bounded and bidirectional are. Had you thought of maybe exposing reversible as a concept?
Do we need a separate concept for reversible?
Well, we don't need it, but my point is that it's what we're used to thinking of.
Right.
And so it was kind of a trip up when I realized that.
I mean, that's an interesting piece of feedback. I suppose like the requirements on reversible would be like can you reverse something where like you don't exactly know the physical position of the end? Like for instance, can you reverse a null terminated string? Well, first you have to find the end before you could reverse it, which, you know, for a vector, you don't have to, you already know the end. So there's a subtlety there, like, do I say that something that is delimited is reversible or not, even though it's like an order n probe to find the end, right? And then, like, the other question is it infinite or not? In which case, obviously, reversing it's going to be hard.
Right.
So there's some interesting questions that need to be solved. You know, like that one, like, is a null terminated string, do we say that's reversible or not? Yeah, in theory, yeah. So whether we need a separate concept for that or not, I mean, that's a matter of taste. I would probably not, because I like to keep this set of concepts as small as possible. But that's my personal preference. Okay. Yeah.
So I just wanted to touch back on the transpose thing. I think I said it wrong when I said pointer. I was trying to say iterator, and a few other people have brought this up. So that's why I came up here all excited, because I think we're thinking about it. And I want to get the code off GitHub and look at it, because I think just coming up here at the mic, my ideas are going to be too off the hip. But what I was trying to say was, it seemed to me from the chair back there that you could just have an iterator that would tell you the beginning, so you can go back to the top. And the idea also was put it at the end. You could just keep track of what you want to put at the end when the sentinel of that side is hit. You wouldn't necessarily have to concatenate it. It could be infinite of infinite ranges and transpose, because you just say, when I reach the end, then I'll go back to the beginning. And you have to just keep the iterator of what's the beginning. And for each one, so you have to keep track of the beginning and current. And on current, you're just do one step and then go to the next. Maybe you'd have to keep another iterator. My point is, it seems that I don't need a vector of all of my rows. I could just keep a few iterators and step them. That's what it seems like to me.
Well, my thinking, and I mean, I would need to sit down with you and work out your idea, because it's not completely clear to me right now. But the way it seems to me is you've got all of these columns, right? And you need to remember your position in each column.
In each one, yes.
And so, unless you know a priori how many columns there are going to be, you need to store n positions somehow, where n is a runtime thing. So that's why I used a vector.
And that makes sense of how it could be solved with a vector.
Yeah.
I'd like to look at the code. Maybe I'll contact you later if I have an actual solution that would work.
Please do, 'cause if there's a way of doing interleaving without
The vector.
iterators holding...
and that's what I meant by pointer. I didn't mean a literal pointer.
Sure.
But yeah, okay.
But I mean, the problem is still true with iterators also, that if you are holding an iterator to a previous element, well, that had better be a forward iterator.
Yes. Oh, I didn't mean previous like leftover
Okay,
columns.
yeah.
I meant previous like at the top. So that, because the interleaving had to go back and then over one.
No.
Okay. Anyways.
Yeah.
Thank you.
Yeah.
Hi. I have a question about the sentinel and how that's specified. Is that just something that has an operator double equals with an iterator, or?
Basically, sentinel, is something that you can compare an iterator to get a Boolean, true or false.
So does that generalize then to just a range being composed of an iterator plus predicate?
It does
as well.
So that is one possible implementation of Sentinel, but you really would like an iterator pair to satisfy the requirements of range. So that's why rather than making iterator and predicate the abstraction.
Okay, so you could make a kind of sentinel out of a predicate, no problem, but you can't.
You can make a sentinel out of a predicate,
right?
But syntactically, I want as much backwards compatibility as possible, so I preserved the syntax using double equals to check whether you're at the end.
Yeah, got that. And another thing is, it's a big jump from input iterator to forward iterator. Do you have any idea about refining the iterator category tags or concepts?
Well, what do you see between input and forward?
Oh, I don't really know concretely. I just know that boost iterator has a lot of these refined concepts. And is there nothing between input and forward?
So boost iterator was an interesting effort at, remember how I was talking about the proxy iterator problem?
Yes.
Boost iterator has its own take on that problem.
Right.
And its take was actually quite a bit more complicated. What it does is it sees iterators, which today are, you've got access and traversal all in a single object. And it's this one object that has all this responsibility. To kind of like break it up, and here we have here is the traversal strength, and here is the access strength, right? So you can specify these things independently. It breaks up the orthogonality of these two responsibilities of the iterator. I didn't want to go there.
Yeah.
I thought the boost iterators model is too complicated for my taste. I kind of like the single object, single responsibility nature of the current STL. And I like the clean single hierarchy that's there.
Okay.
So I tried to preserve that as much as possible.
Got it. Thank you.
Hi. I'd like to talk about performance.
Surprised it took this long for someone.
Yeah, I know. I was waiting for someone to do it. So when you see something like std copy or std like fill, it's usually pretty straightforward to map that to C operations like memset, memcopy, almost like one-to-one, very low level, kind of intrinsic functions. But when I see the ranges stuff, I'm not sure how well that maps to that. And also, another thing is you say it was stateless, but it was allocating like crazy. So Do you have a comment about that stuff?
Sure. This solution allocates like crazy, for sure. It's doing a bunch of string manipulation. It's doing, the interleave. The iterators have vectors. The iterators get copied all over the place. So vectors are getting copied all over the place. This is probably not the most efficient solution to this problem. You know, if you really cared about the performance of formatting calendars to the console, then you'd probably find a different way of doing it. If boost format were range aware, then I could do less string formatting and more just building lazy ranges. So a lot of that allocation would have gone away just by having more modern tools to rely on. So it's a problem that can be solved, and I think it probably will be over time. As for the interleave and the vector, there are ways of solving that problem. Small buffer optimization could help here, or using the template parameters like somebody else suggested, so you can actually tell it how big, so you can statically allocate this stuff. But the thing that seems to freak a lot of people out about solutions like this, or one of the things that freaks people out about solutions like this, is that it looks like, geez, it's like composition and composition and composition. And so you're building this like entire stack of objects that wrap other objects, a million function calls. How is this going to actually perform? Now, if you think about the final solution, I did this, I build a range of dates and then pipe it through all of these adapters, and I get this thing that formats the calendar. Right? This thing is a range. It has an iterator. It has a single iterator that knows how to write a formatted calendar to the console. That one iterator type. Can you imagine how complicated its increment operator is? Its dereference operator is? Could you imagine trying to step through that code in the debugger? Right? It kind of like blows the mind. Like, how much work is actually going on there? It's a lot of work. The thing to remember, though, is that all of these function calls are statically bound, and they are all inlineable, completely transparent to the optimizer. So compilers actually have a really easy time optimizing code like this. It's all inlineable. It really only matters like how high you crank up your optimization level and your inlining depth.
Okay. Thank you.
Yeah.
Hello, slightly off topic perhaps, but at the end of your talk you mentioned STL2. I'm participating in SG14 for low latency, embedded development, that sort of thing, games particularly. And the first thing that springs to mind when I hear STL is the cost of exception handling, and I was wondering if that's the kind of thing you might be addressing in STL2, for example, dual interfaces, which may throw a throwing interface and a non-throwing interface, or that kind of thing.
So the cost of exception handling, I know the game designers take the cost of exception handling very seriously and find that turning off exceptions makes their applications on the order of 5% faster, 6% faster, or thereabouts. So that's nothing to sneeze at, and I understand. I think, to get away from ranges for a second, to talk about exceptions and the cost of exceptions, those comparisons, I think, are a little apples to oranges. If you can turn off exception handling and have correct code, that means you're not actually using exceptions to affect your control flow at all. That means you are checking for errors. Presumably you're checking for errors. I hope at some point you're checking for errors with branches tests. And if turning off exceptions doesn't remove those tests, then you've just removed support for something that you're not using, right? But that means that testing with exceptions turned on means you're testing with exceptions and with checks for error conditions. Whereas if you were actually using exceptions, you wouldn't have those tests. So are exceptions slow? Well, if you use exceptions and a bunch of if statements for testing error conditions, then yes, exceptions can be slow. So what I'm saying is, if you wrote the same application in a totally different way, relying on exceptions and not doing tests for error conditions, then you'd probably find that it's every bit as fast as your program that uses tests for error codes. All of that aside, what I presented here is kind of exception agnostic. Do you worry about exceptions when you call standard algorithms? They don't throw exceptions. So that's really what's going on here. None of my code throws exceptions. It asserts when it finds error conditions, but it doesn't throw exceptions. So I don't think you have anything to worry about in any of the work that I'm doing.
Indeed. The ranges look great. They look lovely. But I think I might mail you privately about exception handling. Thank you.
Yeah, thanks. So I think the session is over. It looks like we have one more question. So I think I'm going to go ahead and take that. Yeah.
Your talk is quite interesting. Do you know if, especially the interleave and chunking thing, I've been thinking for a while that actually structuring data is one of our main problems. In the game industry, to me anyways, the data is the thing, not the algorithms that are causing me so much stress, although partly. If I could define structures in a similar way to the way you're doing ranges, that might be quite powerful, not just the infinite list, but rearranging memory to describe things in that way. That might be very powerful. We have concepts of texture swizzling and things like that, where you rearrange all the bytes so it's cache friendly as possible and things like that. Do you know if there's any things being done in that vein as well?
Well, I'm not aware in particular of anything like that. What I was showing was, like for instance, the transpose. This is a lazy operation. It doesn't actually rearrange the way things are in bytes. So
Agreed. That's why I'm thinking.
So it's not actually going to make anything more cache friendly.
Yeah, exactly.
If you're worried about things like cache, you actually do need to actively, eagerly rearrange things. So having lazy range adapters helps you not at all.
Mm-hmm. But it might help me reorganize my data in a particular swizzled way and define those structures.
Absolutely. So you could use something like this to do a lazy transformation and then copy it in to memory where it will have the correct cache-friendly layout.
Mm-hmm.
So that's something that is a real possibility.
Yeah.
But you have to do the copy in that case.
Yeah, you got to instantiate it somehow. But that's what I mean is once you've done that though, how to codify, like you do the transform offline on one tool and then load it with another tool. How do you? Anyways, I wasn't quite clear on how I could do that at this point. Anyways.
Yeah, I would need to know more about your particular problem.
Yeah. Okay. Maybe I'll talk to you offline then.
Yeah. Okay.
Okay.
Thanks a lot. Okay. Thanks, guys. Thanks for coming.